Hello everyone, my name is Maciej, I work in Wire. We develop a new type of a messenger, secure and end-to-end encrypted. We have a number of client applications, among them Android, which is written in Java and Scala, but also others, each for one of the most significant platforms, iOS, Mac, Windows and web browsers. The iOS client is written in Objective-C and Swift. The Windows and web browsers run on JavaScript under something called Electron. And there's also the backend, written in Haskell and a bit of Rust. I'm telling you that because, well, I'm boasting, but also because it's connected to the reason why we chose Scala. Some time ago, we thought that coding a mobile application should be quite similar no matter the platform. There were different ways of writing UI, but by definition, the UI should look almost the same in each case. And the logic behind it was the same. This common logic part is called Think Engine. The first attempt was to write it in C++. It wasn't the best idea. The life cycles on iOS and Android are so different that in practice, each functionality had to be written twice anyway. The code was polluted with if-else statements, if we're under iOS do this, if we're under Android don't do that, and so on. A decision was made that we split up the code completely. One Think Engine for Android, one for iOS. And since they were now dedicated to their platforms, we were able to rewrite them in technologies better suited for each one. And Scala was proposed and accepted, and one of the main reasons why it was accepted was that Scala is beautifully reactive. A messenger is supposed to transport information instantly across the network. It reacts to the user's actions, composing messages consisting of text, pictures, animated GIFs, audio and video recordings, cat photos, and, in case of Wire, encrypting it and sending it to the server to another user. What it means is that it also has to react to messages and other notifications sent to it by the server. It has to inform the user about a new message or a call. Also, it has to react to Android. From the application point of view, Android quite often acts as law enforcement, and we can't ignore it. We have to react and stop the application, but we have to do it in a civilized way. All data has to be safely written down, resources released, and so on. In other words, we have to be reactive. The way we code is very tightly connected with what vocabulary we use when explaining how the things work. If I start to use the word reactive to describe certain behaviors, in short time I will use this word more and more. Let's extrapolate. If we can talk about the application reacting to external events, then we can also talk about the parts of the application reacting to things happening in other parts. Let's say the user goes to the settings and changes the preferred color. Our application can react to that by changing the colors of buttons and backgrounds. Or a controller may react to a change in the storage and update itself accordingly. Or if the user switches to another conversation and there was a video playing in the old one, the video controller may react to that and stop the video. How do we implement that? In Android and generally in Java, we have callbacks. Callbacks for everything. Let's say there's a simple feature, a grid with emojis which can be added to the text of the message. When the user wants to add an emoji to the message, we have an interface for that with a method called onEmojiSelected. Our cursor view, which has the text field, implements this interface. Then there's an adapter which contains a click listener, and when the user clicks on an emoji, the listener calls that onEmojiSelected method in our cursor view, and then the emoji is inserted in the text. Imagine that instead we can easily implement a way for the emoji grid to broadcast the emoji which the user clicked on, and our text field reacts to this broadcast and adds the emoji to the message. This device for publishing and receiving information is called an event stream. An event stream is an implementation of the observer pattern. It is possible to do it in Java, but in Scala it's much simpler. Instead of an interface implemented by our publisher, we have an instance of a concrete class. We make it into a field of the publisher, and every time a change happens, we inform our event stream about it. On the other end, we subscribe simply by providing the event stream with a function's body. I'm not saying that the callbacks are too complicated, but, well, they are too complicated. By the way, if it looks to you similar to Reactive X, you're right. We are both inspired by the same things, and both systems are implementations of that server pattern. But whereas event streams in Reactive X are truly powerful, ours are quite light. We can map them and filter them, but there's no flat map, for example. And if the event stream was created somewhere in the past and already started propagating events, and we subscribe to it only after some time, we are not able to learn anything about the previous events. We can only wait for a new one. The reason is an event stream does not have an internal state. It only propagates packets of data. For that, in Wire, we have another tool inspired by a similar feature in Haskell, a signal. We can think of a signal as a variable whose value depends on the state of another element in the application. When the state of that external element changes, the value of our signal right here changes as well. We can either react to those changes, and then it works more or less like in the case of an event stream, or we can simply access the current value of the signal when needed. Think traffic lights. We can see the current color and act upon it, but we can also react to the change to that color. We use signals everywhere in Wire in the Android version of the Sync engine, and since our code is free to download from GitHub, you can use it as well in your projects. So, now I would like to talk for a few minutes about a real-life example. What happens when you open Wire and send a message to another person? For the simplicity's sake, I will avoid corner cases and I will oversimplify in a few places. But apart from that, all the code we will talk about here, you can find it on GitHub. We can think of Wire and any application, in fact, as an onion. It has layers. The outer layer is UI. It's the Android widgets and the views. Some of them still use listeners, but we gradually migrate them to signals. Just beneath, we have controllers, which connect UI with the Sync engine. But even within Sync engine, we have layers. Two big ones are services and the Backend's API. The gap between them is filled with the storage. The storage is the pumping heart of Wire. It's where most of event streams and signals originate. Whatever moves in either direction has to be saved, and the other side reacts to the update of a respective signal. This way, we can be pretty sure that no matter what happens, the application is killed by Android, the phone dies, there's an application crash, the data we send and receive is safe. Implement a storage, add signals, and you already have foundations of a mobile application. We will start with the text field used to type the message. The text field is a widget, so we have to use a listener. In this listener, we implement a method which is called by Android every time the text in the field changes. We use that to publish the changed text. Yes, to a signal. No more listeners. The view containing the text field is connected to the controller. One of the fields of the controller is the signal called entered text. This is where we publish our new text. And our first interaction with the person we want to send the message to is the typing indicator. Just as we start typing, the application sends a notification that we are typing something. It's a very simple packet of data, so it's a good opportunity for us to discuss how information travels through Wire. First of all, the controller has to know who are we talking to. In Wire, apart from the very initial state just after the installation, one of the conversations will always be the current one. There is a signal which holds the current conversation ID. We can simply access it. By these few lines of code, we can say that every time the entered text is changed, we want to access our current account, then get the current conversation ID, then access the service which implements how the typing notifications are handled, and then inform the service that we wrote something. Every time we update the entered text or switch the account or the current conversation, the controller will react by calling this method. Please also note the order. We can safely assume that the account changes not as often as the conversation, and that is still not as often as the text update. Otherwise, if for example we put the entered text at the top, with each text update we would also query the account and the conversation, even though they haven't changed. Okay. The user typed the first letter and the controller reacted to it by calling a method on the service. The service creates a request object and puts it in the storage. By storage, I don't really mean the database. I mean also the database, but as well the whole logic around it. The typing indicator is not put in the database, but is held as a Scala object in this logic part. And the fact of putting it there triggers an update in a signal held by a sender in the backend's API on the other side. The sender gets the ID of the conversation and transforms our request into a real post request, and that goes to the backend. The backend is in charge of identifying the receiver of our message and sending it there, either as a Firebase cloud message, FCM, or through a WebSocket. It's either or. We trust our colleagues from the backend that one message will come to us only from one of these sources. However, we consider FCM to be unreliable. Messages sent through FCM have a nasty talent to go missing. WebSocket is more reliable, but it's heavy and it drains battery. So, if WebSocket is on, we can assume we receive all the messages and can simply process them, but if we receive an FCM message instead, we can't be so sure. In fact, we use it only as an indicator that someone wants to contact us, but we ignore the contents of such message. Instead, we perform a fetch, that is, we send a request to the backend asking for all the messages it has for us. Okay, we have our typing message, the receiver picks it up. Please note that the backend does not know which conversation is the receiver's current one. It knows it only about the sender. So it will feed the receiver with all the typing events happening in all conversations which it knows we are interested in. The receiver listens to them all, groups them by conversation ID, and stores them. On the other side of the storage, they are published in an event stream. But an event stream does not have an internal state. This is not how it works, which is good for us in this situation because the user cares only about her current conversation. All the other events are ignored. Now, back in the controller layer, we have something like this. Again, we have a sequence of signals. One is evaluated every time we switch the account, the other when we switch the current conversation, and the third when the list of typing users in the conversation changes. That third line creates a signal on top of the event stream. The signal filters the events in the stream for ones with our conversation ID, and it updates itself with the sequence of users doing the typing in that conversation. That last line is a utility value which tells the view if the typing indicator is visible at all. If it is visible, then in the view we can listen to the signal and then show the animation of a pencil which, for example, writes my name. Let's go back to our text field. Before we start typing, we don't even see the send button. Wire likes a certain minimalism, as in don't pollute the UI with all the possible action buttons at once. So in place of a send button, initially we see a small hourglass. Clicking on it will let us set the time after which the message will disappear. But the moment we start to type, the hourglass is gone and the send button appears instead. Okay, so we have it, let's use it, let's type hello world, and let's click the button at last. Two things happen here. First, we send a message. We access the signal with the current conversation ID, then we access a service for sending messages, and finally we call the send message method on it. When its work is done, then, too, we publish that fact to the event stream. It is then listened from other places in Wire. For example, the text we send also appears in our own conversation. The call to the send message method actually sends a message. The path is similar to the typing indicator request. The service creates a request and saves it, to the database this time. The request is then picked up from the storage by the sender on the other side, transformed into a post request. Well, not exactly. Between the storage and the client, encryption takes place. And on the other side, the message is decrypted and only then put in the storage. But encryption is another layer of complexity, and we would need another presentation to talk about it. The post request, apart from the message contents themselves, carries some metadata. Among them, the ID of the conversation and the timestamp. When in the receiver, the message is written down to the storage, it is within the context of the given conversation and ordered by the timestamp. On the service side of the storage, We have a message cursor, which is an abstraction over the database's messages table. In the UI, we have a separate view for each message, but since there are so many messages and most of them are not visible in any given point of time, we don't want to create and destroy these views. We want to reuse them. For that, in UI, we have a wrapper which contains the cursor and computes a visibility window, reacting to the events such as the user switching to another conversation or scrolling up or down. That wrapper interacts with the Android's recycler view to display the message. There is at least one more tiny detail to talk about. In the same time we send a message to another user, we display it in our own conversation. It can be in one of four states. First, we display it with a footnote sending, indicating that the message is in the process of being sent. When the message is sent, we receive a confirmation or an error. If it's a confirmation, we add a small note sent to the footer. If we receive an error, we display the error message in red. If the message is received on the other side and then displayed, the receiver sends back a receipt. Just as the typing indicator, a receipt is a small message without any actual content other than the information that the original message was displayed. It goes all the way back through the backend to the original sender. Finally, the view on the sender side gets notified and reacts by changing the footer's text to delivered. Mind you, all this is only about sending one text message in a one-to-one conversation. Not a call, not a video conference, not a group chat. And in all this, we heavily rely on signals and event streams. Doing the same only with callbacks would be an order of magnitude more complex. If there is one thing I would like you to remember from this talk, it's that a good technology is a technology which lets us keep things simple. The human mind may hold only so much complexity. If our application is already complex on the low level, we will struggle when it comes to adding to it more high-level features. We will not be able to remember all the details, we will forget about corner cases, and it will take us more and more time to work with the code. There are two ways to avoid that. First, keep away from abstractions if they are not actually useful, but only look smart. Of course, it may happen that in the future these abstractions will become useful, and that's why it's nice to use a language which makes it easy to refactor the code. Scala is awesome in that respect. And second, if we are able to encapsulate this complex logic really well, possibly with use of syntax sugar and special features of our language, then we can actually forget what's inside. We can throw it away from our minds, making room for more high-level stuff, making our application more robust and more epic. This is all. Thank you for your attention. I hope you liked it. If yes, please leave a comment below.